So if we want to solve force-based problems, let's look at how to set these up. And again, it's going to be reading a problem, and I'm introducing you to depths, which is basically what you're doing is you're going to make a diagram over here, and these are often called free body diagrams. And all that means is we just want to look at the object and the forces acting on the object, direction and size. So if I want to show this, I know that I have a 70 kilogram skydiver and she encounters 200 newtons of air resistance. Now that's a force, and air resistance is always going to oppose motion. So once you know the way the object is going to move, air resistance will be the opposite direction. So if I have a skydiver, my diagram is going to start like this. I'm going to be very, very non-artistic. The dot is the mass. And now it says she falls, so I know she's going this way. Now I'm going to draw force arrows that are going to show that the direction of the forces and the size of the forces acting on this object. I know it's falling down, so then I know one of these forces is this way. I'm going to write it here and say, I usually start to label these, and that's a bad pen to use because you can't see it. But if I call this one FAR, force of air resistance, I know that this acts with a value of 200 newtons. And it's acting in an upward direction because it's opposing the falling direction, so I put that as a positive 200. There's another force on this because we know that the Earth pulls on everything, so you're also going to have a gravity vector or a weight vector, which is Fg. And we know what the size of that's going to be. Okay, it's going to be the mass times negative 10. So you're going to have 700 newtons force down, pull by the Earth, and an opposition force of 200 up. So once you've identified these are the only two forces, and if you know the size of the forces and the mass, you're going to be asked to determine the acceleration. Well, guess what? I don't see anything about motion here. I see Newton's laws. So then what I'm going to do is I'm going to say, well, the only Newton's law equation I know is, if we look at the second law, the acceleration is based on the net force acting on the object and the mass of the object. Well, guess what? Now we start to see that the net force is a combination of more than one force. These are two vertical forces. We can add these together, just like mathematically. So I'm going to write this out in a little more detail, and I want you guys to be doing this too. I want you to basically say the net is the sum of the air resistance force and the gravitation force divided by the mass. And that's going to be the acceleration rate. Now basically at this point, now we go to plug in. So I'm going to solve for the acceleration. My air resistance force, I'm just going to by default show it as a positive just to keep things straight. Because this is an addition every single time. The minus is direction. You don't do a subtraction. You add the vectors. The minus and plus is built into the vector. So the gravitational force is a negative 700 newtons. And we're going to divide that by 70 kg. So now we're negative 500 newtons is the net force. In the tug of war between the two, we only have 500 newtons left pulling this thing down, divided by 70 kg. And now I'll go to the Casio. Negative 500 divided by 70, and I get negative 7.14 meters per second squared. So look at this. We know that free fall acceleration is negative 10 meters per second squared, right? And it's falling slower than that, which means something had to impede or counter or oppose the gravitational pull, which is what air resistance does. So your answer is she accelerates at this rate. The negative tells you she's moving downwards. Clear as mud? Okay, next one. We're going to use the same situation, but now we're going to change the air resistance. As objects get faster and faster, the air resistance builds up on them, the size of the air resistance. So this is still going to be 70 kg here. Well, we haven't changed the weight of the person, so this is still going to be 700 newtons down. And we know the force of air resistance now, FAR, is now 500 So it has a little more substance to its opposition. Same layout again. What is the net force? Just substitute in. Again, I have the FAR plus FG, and the air resistance is 500 newtons added to a negative 700 newtons. So 500 up, 700 down, divided by 70. All right, now I'm just going to kind of, technically, guys, this goes here, and then you get negative 200 newtons. So you only have 200 newtons down acting, divided by 70 kg. And you're going to see it's going to accelerate a lot less. So negative 200 divided by 70. Acceleration is negative 2.86 meters per second squared. The first workbook page you're going to see focusing on this is A23, and this video might be shown before or after that, but you're basically looking mostly at this. There is one other example I do want to show you, because it has to do with, what if we don't deal with skydivers? What if we deal with an elevator or another force? How does this lay out? And this is kind of a cool one to look at. So if we have an elevator, and I'll have a tendency to kind of draw this stuff out. So if I get this elevator over here now, and elevators move mainly by cables. So, you know, there's going to be an upward force on this that's going to move this elevator up and down. It's going to work against gravity. So I know the mass is 1100. So if I kind of make this down to the way I've done it before, I'm going to say M is 1100 kg. Now I know automatically I can get the gravitational pull here. 1100 times negative 10. Okay, you should be good enough at this point. You're 11,000 newtons down. Now there's an upward force on this because it says it accelerates upward. The upward force has to be larger than the downward force, otherwise it's not going to go up. It's not going to accelerate upwards. So we don't know what this is. So this is taking the second law, and I want to figure out what this is. What's the acceleration? So I'm going to write it out again. Now we know it's the net force, so I'm just going to say this is the upward force plus the weight, the gravitational pull, divided by the mass of the elevator. That's my equation. Plug in. Now notice this is different. We're not solving for acceleration, so you got to do some more algebra here. To give you the acceleration, I'm going to write it very, very specifically. It's positive 3 equals. We don't know the upward force. We do know the gravitational force. 11,000. 11,000 down. And then the mass is 1100. Now be very careful here, guys. You got to work the algebra, so don't just start jumping in until you know what you're doing here. I look at this and I can see cross multiplication about to happen here. Or multiply 1100 both sides. I know it's 1100 kg. I'll put the units in here. Plus 3 meters per second squared. That's going to give me newtons for an answer. So 3,300 newtons is what that comes out to be. We don't know the upward force, but now we know that this is 11,000 over here. Isolate the unknown. Add 11,000 to both sides. All right, and if we look at the math together here, now remember this is 3,300, so the 3,300 goes here. So we are 14,300 newtons is the size of the upward force. And think of it this way, guys. This should make sense. Because if you had an upward force of 11,000, this thing shouldn't move or it shouldn't accelerate. So you have to be greater than the 11,000 in the positive direction to make this thing accelerate upwards. So you are. Okay, you're 3,300 newtons over that 11,000. But that would be how you would solve for an unknown force. It is really, really important that you don't do this and try to solve that way. Because this is made up of two things, one you know, one you don't. So I'm going to be really, really, really adamant about making sure you write this equation out, however many forces there are, before you plug in and solve. That's the end of today's lecture. Solving multi-force problems, we focus only on vertical, and then next time we'll look at horizontal. So I hope that helps out. Have a good day. Bye-bye.